Hello, everybody, and welcome to Circuit Lab Practice number 2. So this one is going to be on static electricity, conductors, inductors, and making measurements. And so I hope everybody here has a great time. Right now we've got 8 viewers. We expect a few others to appear as we come along. Hopefully you've done both practice number 1 and practice number 2 and had some experience working with the homework generator. We're also going to talk a little bit about making measurements, which I think is going to be really interesting. So before we start, just remember, this is only my personal opinion as a national event supervisor. This is not meant to replace any of the coaching that you get from your own coaches, or anything we say here actually doesn't supersede the rules on the national website. So just please keep in mind, this is all my opinion. Okay? So as we start off, I'd like to ask everybody on here, please let me know if there's any issues that you've had with the first 2 practices or any issues you've had using the homework generator. And please, and if it's all working well, say that too. So just type it into the chat. Oh, Coach Chalker says it's been working wonderfully. I'm glad to hear that. Coach Chalker and I actually jointly coached this and other events, other physics-based. It's been working good. Okay. Are there any questions that anyone has? Okay. Well, with that, I think what we'll do then instead is that we'll just review some of the main concepts. Wait, okay, here we go. How do you tell how many electrons flow through a resistor? So there were 2 resistors. There's more resistance in one, less electrons would go through that one. And the other question was, how do I feel about LSU football? And after winning against the Georgia Bulldogs, which is a great team, I feel very good about LSU football this week. We've got some challenges up ahead. We're not playing near as well as like Ohio State or Alabama or any of the teams that are right up there, but we're right behind them. So, all right. So let me talk about how you know how many electrons go through a resistor. Okay. And with this, I'm going to use the whiteboard for the first time. So hopefully that works well. So you'll have to tell me if the whiteboard is very visible. So that I'm going to turn the light on to the Here we go. So here we go. We're going to put this on the whiteboard. So the way you look at this is V equals IR. Okay, that's really the most important thing, and this is Ohm's law. Okay. I always write that down first before I write anything else down. Now, I is defined as the current which is also defined, which equals the amount of charge over time. So this will be in coulombs, the units are coulombs per second. So the question is how do I figure out the number of electrons that go through something else? So if I have a current of 1 amp, that's equal to 1 coulomb per second. Okay. And now I'm going to ask everybody to look up how many coulombs in a single electron. So how many Now this is going to be interesting because we haven't covered this. There's not the specific formula, Mr. Patel, is Ohm's law. So there we go. So T answered that it's, and I remember this being very near, is 1.602 times 10 to the minus 19 coulombs equals 1 electron. Okay? Right? So I've got 1 coulomb per second, right? So that means that that's the same as, so this 1 electron is equal to that many coulombs. But I got to solve for the C, so I divide both sides by 1.602 times 10 to the minus 19 coulombs. Well, actually, we don't have to do it by coulombs. 1.602 times 10 to the minus 19. And now I'm going to go grab my calculator. And so I take 1.6092, hit the 1 over button. And so 1 coulomb is equal to 6.24 times 10 to the 18 electrons. So there's a lot of electrons in a single coulomb. Okay? So if I go back here to this question that I had before, okay, that's equal to C, 1 times 6.24 times 10 to the minus 18 electrons divided by seconds. And that's 6.24 times 10 to the minus, or 10 to the 18, sorry, not 10 to the minus 18, 10 to the 18 electrons per second. And that's how you solve that one. Now you will notice I use scientific notation for that. For those of you in middle school who've never seen scientific notation, it is something you are going to have to learn. The reason why is we're going to deal with very large and very small numbers. So that 10 to the power gives you the idea of the number of zeros or the number of places to the left of the decimal place that it works. I would recommend that you get together with your math teacher or your coach or another mentor to really practice with scientific notation quite a bit. Mr. Patel, did I answer your question? Oh, outstanding. Okay. Next question. Wait, before we go any further, was that easy to read on the whiteboard? That was the first time we tried the whiteboard. Oh, super, super. I'm glad to hear that. So we're going to be using that quite a bit. Okay, Dakiel Williams said no. Everyone else said it was good. Oh, my arm was in the way while writing. Okay, so I'll have to keep that in mind. What I may try to do is I may try to write from the other side to make that a little bit easier. But the key is, if you notice, generally speaking, the most important formula, and the formula that I started out that problem was Ohm's law, V equals IR. That's the one that you need to practice again and again and again to know. Then I knew that my current was in coulombs per second. So then I just had to figure out how many electrons in a coulomb. Once I had that, I could easily then convert amps into electrons per second or coulombs per second. Well, amps are defined as 1 coulomb per second. So I just had to convert it over to electrons. Okay. What I may also try, do you think I ought to try a bigger marker or thicker marker? Will that help? Or is it mainly the arm? Okay, so I'll keep it with a smaller marker, but I'm going to look out for the arm. Okay, has everyone done the homework generator problems level 1 VIR? And if you have, Who here can get through it 100% with no problems? Who here was having problems? Okay. Well, I tell you what, who here, okay, wait a second. So, Mr. Milarski, you looks like you're having some issues. What were the problems that you were experiencing? Okay. Well, what I'm going to do here real quick is I'm going to bring up some no issues. I could do them just fine. Very good. So once you get 100% on it, time yourself. And then you want to do it just as accurate, never missing a problem, but you practice doing it faster. Once you're doing it really, really fast and it goes like that and you're not missing anything, you're ready for the next level. Okay. The whole purpose is to give you more of an opportunity to practice over and over again such that you're not thinking about that. Okay. So if we look through the slides, okay, we look through the slides that we had before, you'll notice that we mainly talked about the basics of electronics, the important terms. We talked about how a circuit is always in a loop. We talked about static electricity and how its electricity doesn't flow, and how certain types of materials, like let's say wax, usually has an excess number of electrons, and things like wool cloth usually has an excess number of holes. So if you were to put a wire between an electron or between the wax and the wool cloth, the electrons would flow from the wax to the wool cloth, and the holes would flow from the wool cloth to the wax until they equalized. Okay. You'll also notice, okay, that things that have the same charge repulse each other, and things that are opposite attract. So positives are drawn to negatives, but positives push away positives and negatives push away negatives. Okay. We also talked about how electrons move or conduct, and it's much like a series of marbles going through a tube, such that as one electron or hole goes into the tube, the other one is pushed out. We talked about circuits. We talked about which direction does it flow, and we talk about how in this case, the conventional current flow goes from the positive to the negative around, but the electrons are actually flowing from the opposite way. We talked about how to talk about water, and we talked about how to identify batteries. And so one of the problems was to identify batteries that are available out there. And so what I went out and did was I went out and I grabbed some old batteries. So here you go. Here are some common batteries. Does anybody know what type of batteries these are? You can read. It's actually sort of easy. There are 9-volt batteries. That's right. So these are very common in electronics, smoke detectors in particular. Okay. Now, generally speaking, a battery is designed such that it will keep its charge for a long time. Okay. And over time, though, the charges get together, the chemicals degrade, and so therefore, and the terminals may corrode, and so you lose voltage over time. Also, if you use it a lot, you'll actually have all the electrons go to the positive side and all the holes go to the negative side, and it becomes very neutralized and the voltage goes down. So a very easy way to figure out if your battery is dead or not, okay, is to check the voltage. Okay. And so what I did was I went out and I pulled out my, hold on a second. We got some questions before I get off into that. Okay. Are there any specific materials we should know the charge of? Well, I would recommend that you look up and have in your binder which materials generally have excess electrons and which materials have excess holes. Okay. And from that standpoint, what I'm getting at is, like, you remember how we were talking about the wax and the wool cloth? That's a very common type of question, where they might ask you, okay, in Ben Franklin's test where he would take a glass rod and rub the wool cloth on it, which one, what were their charges afterwards? Because one was going to be positive, one was going to be negative. So look those up. But I would say the ones that I provided you with, like silk cloth, wool cloth, glass rods, wax. Another thing that's a real popular one, and that was why I put it on the homework, was why do you try to, or what are some of the things you do to get rid of static cling? You know, whether it's putting in extra moisture, okay? You know, like your hair is standing on end, so you grab some water and you throw it in your hair, and it tends to do well. Well, there's also other types of chemicals that you can use, like a dryer sheet. A dryer sheet is famous for being able to reduce the static cling, okay? And yes, believe it or not, if you're having a real staticky hair day, you can actually rub a dryer sheet in your hair. You'll come out smelling really nice, but more importantly, you'll get rid of the static cling. There's also a lot of questions about, you've got a static in a balloon. Why does it stick to the wall? By static cling. And what ends up happening is that the balloon ends up getting very, very charged. Okay. In fact, it becomes so charged, in fact, that when you stick it on the wall, it actually repulses the other charges so much, it makes the wall have a charge, a slight charge, a very small charge. That's why it can only hold up a balloon. You couldn't use that to, like, hold up a painting, if you will. Okay. But it's also why that if you then take the balloon and let's say you dipped it in water, or let's say you pull the balloon off, okay, and try to put it back on, a lot of times those charges have equalized. The balloon doesn't stick anymore. Okay. How much should we know about the history of scientists like Tesla, Volt, Ohm, etc.? Probably more than you would think, but not as much as you fear. And what I mean by that is that every event supervisor is going to ask different numbers of history questions. Okay. Those of you who've looked up some of my old tests on Scioli know that I tend to ask about 10 history questions. That's it. And they're usually pretty simple ones. Why? Because while I think the history is important, I don't think it's nearly as important as being able to solve the problems. There are other people that may have page upon page upon page, or it may be a tiebreaker. Okay. So my recommendation is try to compile mini biographies, if you will, of people like Volt, Tesla, etc. Okay. And put those in your binder. You don't have to know everything verbatim. That's why you have a binder, but do highlight the important parts. Let's see. In the future, would you consider doing streams on Division C only, rules, requirements, RC circuits, and op amps? Absolutely. We are going to do those. And in fact, those are going to be some of the later ones, probably in late November, early December. If you've already got to a specific topic, you've got my email there, or you can actually type on here who all would like to go ahead and do the op amp review. We can do it. I don't have a video on the op amp. I'm actually, as soon as we're done here, I'm going to do practice number 4. But you'll notice a lot of the Division C topics don't start until the end. So like the first, I think 10, 11, 12 are B and C. And then after that, it becomes C only. Should you know anything about rechargeable batteries and how they work? Absolutely. And in fact, we're going to get in a little bit more into batteries in the next practice. But it's very important to know, like, how lithium batteries work, why they recharge, why you pick lithium. Okay. It's important to know why you would pick acid why would you have a lead acid based battery? For history, should we gather information on someone like Ampere, who isn't in the room, but just as a precaution? Well, Ampere is in the room, is in the rules. Okay, you got to remember what the rules say for history. Historical perspective of the discoveries of electricity and the key people involved. Ampere is definitely one of the key people involved. So Ampere would be very, very fair game, just like Michael Faraday, Benjamin Franklin, etc. And Coach Chalker recommended to collect extra history. You have no ideas what questions they're going to ask. Okay, let's see. Also with a binder, it doesn't hurt to have extra documentation. Couldn't agree with you more, Coach Chalker. Just always make sure that you don't put so much in there that you can't get to it quickly. At the beginning of next practice, we're actually going to start it off with a binder check. And the first thing I'm going to ask you is, have you found the rules in your binder? The second thing I'm going to ask you with Ohm's law. And then I'm going to get tricky. Okay? And a lot of those are going to be, I'd like you to find your page on Ampere. I'd like you to find your page on Gauss, on Joule, or Joule, sorry. All right. So with that, and any experiments today? Well, actually, we're going to talk about measurements. So you remember I talked about this particular battery here. It's a 9-volt battery. It has 2 terminals, one slightly smaller, one slightly bigger. Okay. Both of them are on the same side. You'll notice the terminals don't touch because then they would be shorted out. Okay. Now, the other thing that you'll also notice about this is that they're different shapes, and this makes sure that the polarity is set such that one of these is the positive and one of these is the negative. Okay. So one terminal is positive, one terminal is negative. So if I was to point to the larger terminal here, is that the positive or negative terminal? Please answer. Let's see who's going to be the first one. Big one. I got 1 vote positive. Positive. Mr. Pierce says negative with a question mark. Mr. Patel says negative. Got another positive. Positive. How do you measure volts? Negative. Positive. Well, I will tell you that those of you who answered negative or positive, about half and half. Simon K, positive with a question mark. Mr. Malarski, negative. Okay. Now you'll notice I picked this particular battery, not the other one. And the reason why is because the other one actually had it marked on the outside. So you'll notice that on the side here, it'll show you that the bigger one is in fact negative. So the bigger one is negative. The smaller one is what? What is the smaller terminal? Is it positive or negative? I got a negative. I got another positive. I got another positive, 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 positive. All right. And in fact, it is positive. Now, don't ask me why they picked the smaller one to be the positive, because if I was doing it, I'd make the bigger one positive. That's just how they did it. You'll also notice that one's male and one's female. That's to prevent you from ever accidentally hooking up a 9-volt battery wrong. Okay? So you'll notice that this one is more of a male connector and this one's more of a female connector. And then when you attach it to a 9-volt connector, it's that way. Okay? So now we're going to talk about another type of battery. This type of battery. Who here can recognize what type of battery this is? Double A, double A, double A, double A. Okay, very good. How many volts is a double A? I got a 1.5 volt question mark, 1.5 volt, double A, 2, 3, 1.5. Well, it's supposed to be a 1.5. I'll tell you that much. So generally speaking, most of these types of batteries here are going to be 1.5 volts. And the reason why is that they really got good at making 1.5 volt cells. So this is like a single cell battery. I put 2 of these batteries in series. I got 2 cells, 3 volts. I put 4 of them in series. I got a 4-cell battery, 4 volts. Okay. I put 6 of these in series. I got a 6-cell battery, 9 volts. Wait, 9 volt. You'll also notice that a car battery is 12 volts and a marine battery is 24 volts. Okay, now you'll notice that one side has got a little nub on it and one side's got a flat end. The one with the nub on it is at the positive or negative terminal. The one with the nub on the top, is that positive or negative? Okay, we got 2 positives, a negative, positive, 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 positive. Okay, well, very good. So we will look, and lo and behold, it is in fact a positive. So you'll notice that with these types of cylinder batteries, there will always be one side that's flat and one side with a little nub in it. Okay, the side that's flat will always, always, always go against the spring. So the spring will always be the negative side. Okay, so if you're ever loading one of these into an electronic device, you always load it in with the flat side towards the spring, and then this nub allows it to push down, usually against some force, to hold it into place. So this will always be the positive, and this will always be the negative. Now, some of you had asked about, are there going to be experiments today? No, but there are going to be measurements. So I went down to Harbor Freight and for $6 purchased a digital multimeter. This is a $6 digital multimeter, not the best in the world, not horrible, but I will tell you, it's a real common one that is used because they are so cheap. And let's face it, if I got to do 10 stations, $60 is better than putting $50 ones. Okay. So what happens is that the first thing you do with a multimeter, okay, is that I will look at the multimeter, okay, and I will look and see how it's set. Here's DC voltage. Here is resistance. Here's AC amperage, okay, capacitance, and DC amperage. We're not going to make any measurements using the amperage settings because it's actually quite distance. You say multimeter to practice, or a voltmeter and amp meter. Well, if you get a voltmeter and amp meter, you can use those, okay? Amp meters are difficult to use, and you don't find them very often because you can actually blow out the fuse real bad in them. But you will find, please move the tool up. Is that better? Thank you. Okay, so right here is the DC voltage, and here is the resistance. Right over here is where we plug in the leads. You'll notice that I put it into the voltage and the resistance, the red one here in the COM, and then the black in the COM. So if I wanted to measure amperage, I would actually remove this lead here and stick it into here. You will find that I never do that because I don't like blowing up my machines. Okay, so this thing, as long as I use this for less than 250 volts, I'm good. So then I turn it on. Okay, right now it is set up to measure resistance. Okay, at the end of these leads, okay, you'll notice I've got these guys here, and they're really sharp so that you can get into whatever you need to measure, but I can measure my resistance among my leads, and should be very close to 0. And keep in mind, this is 0 kiloohms, okay? So it's really, really a small amount of resistance, okay? But instead I want to measure voltage. Okay. So I flip it such that it is measuring in the 20 volt range. Okay. So anything about 20 volts or less, it will work well on. And you'll notice that if I measure it now, I put the two leads together, 0 volts. Very good. All right. Now we're going to see how well this works. So hopefully you can see it. So I'm going to take the 9-volt battery, and I'm going to put the black against the negative terminal, and then this against the red terminal, and I get about 9.33 volts. Very good. Now we're going to try it again with this battery and see which one's got more juice in it. .2. I could already told you that because this one actually was already starting to have issues in my smoke detector, so I had just taken it out. Now, this is a pretty fresh 1.5 volt battery. Now I'll put it here, so I'm measuring from one terminal to the next, and you'll notice it's 1.66 volts. Okay. So that means that this puppy is usually pretty good. Now you say, well, gosh, I thought you said it was 1.5 volts. Well, it's about 1.5 volts. And in fact, they usually put a little extra juice in every battery. Like if you go out to your car battery and it measures, say 12 volts, you go out there, most of them are going to measure 13, 14 volts. Okay. Were you able to see it that last time? Mr. Pierce suggested I could lick the top of a 9-volt battery, tell you how strong it is. I will never recommend that, but I have done that. And actually, all that will tell you is that it's got enough juice to shock your tongue. Okay. Very good. Okay. Now, since we already got the multimeter out, I thought I would show you guys what a resistor looks like. Now, this is a very, very small resistor. Okay. So if I look at that resistor, it's a 1/4 watt resistor, which means that it can only handle a 1/4 watt before it burns up. And yes, I have burned up resistors before. Now later on, we will learn how to look at those colors and be able to identify exactly the resistance. So what we're going to do here is that we're going to take this resistor with these leads, okay? So I've got a white lead here connected to this side of the resistor and a yellow lead connected to this side of the resistor. I'm going to hook them into my multimeter. Boom, boom, boom. It doesn't matter which way I hook it up because whether the electrons are going left or right, the resistance is pretty much the same. Okay. And now what I'm going to do is I'm measuring the resistance here. So I turn it to resistance. And it's set for kiloohms. So this says that it's 97.9 kiloohms. Oopsie daisy. Is that better? 97.9 kiloohms. Can you see that? Okay. So what that means is that this particular resistor is 97,900 and some odd ohms. Okay. Now, why is that? Now, when we get to resistors, we're going to learn that there are some standard resistor types. Okay. And guess what? One of them is 100 kiloohms. And so what that means is that was a 100 kiloohm resistor. You'll notice that it was well within the tolerance, which you will learn when we learn markings. That was within 5% of the manufacturing tolerance. Part of the reason that I like to use kiloohm resistors is because that way I can use these batteries. Okay. I never have to worry about getting close to that 1/4 watt range. Okay. Because there's just not enough current. And then also, even if I left it on overnight, it won't drain my battery. It won't kill my battery. So there's a lot of reason why I like to use high resistors. Okay. Use low resistors, you get higher current, but as we will talk about, power is equal to I squared R. Well, if power equals I squared R, that means that every time I get more current, I'm going to use more power out of these puppies to the square. So like it's a big difference to go from 0.1 amps or 100 milliamps and 1 amp. You think, oh, it's 10 times greater. No, it's 100 times greater. So if it drains my battery in an hour at 1 amp, it's going to drain my battery in a tenth of an hour at 10 amps. How much voltage will burn up the resistor that you used? Okay. Now, by the way, there was a question that we sort of skipped earlier. I'm going to try to see if I can scroll up on the questions here and see what that question was. I think it was Ty's Extra had a question. Does anybody still have a question before we go on to solve the power problem? I noticed there was a minus sign on the measuring device. Does that mean that the device decided it was close enough to the measurement? No. If there is a minus sign, it probably means that you've got negative voltage. Okay. Remember, if I measure voltage from here to here, it's going to be a positive voltage. But if I actually flip the measurements and went from here to here, it's a negative voltage. Okay. There's nothing wrong with negative voltage. It just means that in reference to each other, one side's bigger than the other. And if you swap them around, the difference is still the same. Now you will notice that when you're waiting for it to be attached, sometimes it will blink. Sometimes it will say OL. I think on this one it says -1 in sort of a funky way to say, hey, you don't have anything hooked up. You're overloaded. You've got an open circuit. I can't really measure the resistance. Okay. So the question that we had was how much voltage will burn up the resistor that we used. And so we'll go back here to the whiteboard. Now, who can guess what's going to be the very first equation that I'm going to write up here? I think you all know it's V equals IR. Oh, sorry, I put that back a little bit too much. So, okay. And the question was, what's the voltage that would burn that up? Now, there's another equation that you should all know, which is P is equal to VI. So this is how you determine in a standard circuit how much power you have. Okay, if you know the voltage and you know the current, P is equal to VI. So this is a power. And remember, this is in volts. But this right here is in watts. Okay? And what power is, it's the amount of energy over a given amount of time. So if you hear like horsepower, that's how much work a horse could do in a certain amount of time. Okay? So it's a measure of work over time. It can also be used to determine how much heat is produced. Okay. So what we say here is that P is equal to VI. Okay. Now the question is how much voltage would it take to burn that up? Well, I got V equals IR. I don't know the current. But if I say I is equal to V over R, that's another way to state Ohm's law, right? So if I take this I and replace it there, then P is equal to V times V over R, or V squared R. That's a really important one to know. and I would keep that one. Okay. Now in our case, okay, so we know that V squared R. Okay. So if I had a 9-volt battery, V squared over R. Somebody should have caught that one. Okay, so we take 9 volts squared divided by 100 times 10 to the 3 ohms. Okay. So I'm going to put that in the handy dandy calculator. Okay. So 9 squared is 81 divided by 100 to the third power. And that's the number that I get, which is 0.00081 or 8.1 times 10 to the minus 1, 2, 3, 4. And that's in watts. Okay. Now, what that tells me is that's 0.8 milliwatts, and that's a lot greater, or that's a lot smaller than 0.25 watts. Okay. So the question was, what was the voltage that would take to burn it? Well, we know 9 volts wouldn't do it, and that's why I picked it, was I wanted to pick something that wouldn't burn it. So now if I know the voltage and I know the maximum power, I can figure, and I know the resistance, okay? If I know the resistance and I know the maximum power, I can figure out the voltage. So using this equation, P equals V squared R, okay? That's the same thing as saying V squared is equal to PR, right? So that's the same in our case of saying 1/4, 1/4 times 10 times 10 to the 3 ohms. And that's watts and that's ohms. And so that equals 25 times 10 to the 3 volts squared. So I enter in 25 to the 3, and then I take the square root of that because I want to make that into V. And V is equal to 158.1 volts. So in theory, my little resistor there could handle 158 volts. Well, I know I don't have anything in the house that's 158 volts DC. So that's why I picked a 100 ohm resistor. How do I know the maximum power of a resistor? By different sizes. So I bought these from Radio Shack. By the way, you can find them online now. You can find them. In hobby stores. And what you'll notice is up here at the very top, it says 1/4 watt resistor. Okay. When they're about twice this size, they're 1/2 watt resistors. And when they're 4 times this size, they're full watt resistors. And those are usually the sizes. They do make 1/8 watt resistors, which are itty bitty ones. Okay. I don't like using those because they're real likely to burn out. So you'll notice that these are the mega ohms. So this is 1 million ohms. And these right here are kilo ohms. So this one has 1,000 times more resistance than this one. And you'll notice if they didn't have color on them, we wouldn't know what they were because they're made exactly the same size. So, okay. I noticed there was a minus. Okay. So that's how you know the maximum power of a resistor. Okay. Are there any other questions? So one thing I would recommend is that if you go online, you can purchase very inexpensive multimeters. But keep in mind, the more you spend on a multimeter, usually the more accurate they are. But I will tell you, this $6 one from Harbor Freight, which is usually one of the cheaper ones, will get you through everything you have to do in Circuit Lab. It really will. It's very, very close. Now, quite often, when I'm doing these at really nice colleges, like when I did at Wright State, they gave us like $500 multimeters to let the students use in the lab, and those things are accurate to like 6 decimal places. Keep in mind, normally 2, maybe 3 decimal places is all you'll ever need. And note that Harbor Freight multimeter really isn't super accurate beyond about 2 decimal places, about 2 sig figs. Right here is my personal multimeter that I use quite a bit. It's called a bench style multimeter. You'll notice it still has the leads plugging in over here. Okay. You notice I hardly ever use the amperage one, but it can measure actually quite a bit more. But I always set it up to measure voltage or resistance, and I almost always keep it on DC. There are a few times that I'll make measurements on AC. You will never need to make measurements on AC as part of Circuit Lab. It's just too dangerous. And part of the reason that it's so dangerous is that because the power comes in as a sinusoid, it's always going back and forth. And it's that change in voltage, if it hits right on your heart, that's when it can cause problems like your heart stopping. Okay. And that's why DC voltage, while you can get a good burn from a DC voltage, it usually won't cause you to your heart to stop. The other thing is that some of the AC voltages, especially before it's stepped down, are really, really high. You're talking about hundreds of thousands of volts or whatever. And then if you get hit by that, it's like being in a human-sized bug zapper. Okay, we explained the basics of the Wheatstone bridge circuits. They're normally on the national test, right? Well, that all depends. As an electrical engineer, I love the Wheatstone bridge. It's got a great place in my heart. That's actually in a few practices forward. But basically the way a Wheatstone bridge works, okay, is through voltage division. And what you do is you get a couple of components that are really high resistance, and you get one component that you can vary. And what you find out is that you can usually measure voltage real easy. So if I'm putting a particular voltage across that Wheatstone bridge, okay, once I get the bridge balanced, okay, I can very accurately know the ratio between the component I'm testing and that really, really well-known resistor. So you remember I told you that one resistor was plus or minus 5%? Well, they'll probably pick a resistor that's plus or minus 0.1%, okay? Like it's right, super accurate. And so when I get it balanced just right, guess what? I know then that exactly what the ratio is. And since the one thing is known to like 0.1% or even better, I can very accurately measure the resistance of the resistor. It's not used very often now. Pretty much everything's gone digital, but it is something that I have seen. And I do believe that that's only division C. All right, let me double check. It's not mentioned, so it could be division B or C. But again, that will be covered on later. Mr. Patel? All right, any other questions? Why is another reason I would tell you to never lick a battery? Does anybody know why you wouldn't lick a battery other than if I did it with this one, it might shock me? In fact, we know it would because we know it's got 9 volts in it. Let's say I could be assured, like in this case, that my tongue would only touch one side. All right, current shock risk. But you see, if I only touch this side, it wouldn't cause the current shock risk. The reason is that these batteries have got some pretty bad chemicals inside of them. Okay. And so if I put my tongue on the battery, and I hate to say it, happens a lot when you try the little test here. Again, I don't recommend it. Really don't recommend ever putting your tongue on a battery because, again, they've got acid and other bad types of stuff. They got lead, but mainly they got acid. And that acid will occasionally burn through the can or will burn through the rectangular block. And then you'll taste a little acid on there. Well, you're putting battery acid on your tongue. And I'm here to tell you it is a bad idea. There's a reason why they say don't swallow batteries or anything like that. And so really, just going back to that, do not do any of that. And I'll tell you, if you handle a battery that has got corrosion and you see, and it's like split on the side and there's stuff oozing out, be very, very careful with that. And make sure you wash your hands with that, because one of the things you don't want to do is you don't want to get it on your hand. Okay. Later, you're not thinking about it. You rub your eye or whatever. Now you got battery acid in your eye. Very painful, and you'll have to wash it out, and you need to go see the emergency room very, very rapidly because your eyes are just too important. Okay. I'm just trying to look through so we talked about how to make measurements. Okay. We talked about the metric prefix scale. Okay. And I sort of showed you sort of the key ones. You'll notice they go by threes. So as a general rule, whenever we're talking, this is very important. When you're talking about resistance, you're usually going to be talking about kilo ohms, mega ohms, even giga ohms, etc. Okay. When you're talking about current, it's not uncommon to almost always be talking about milli or micro amps. And the reason why is that little small amounts of amperage are usually what these little batteries here can handle. Okay. However, if you have a big circuit that can consume a lot of power, it's not uncommon to have high amperage. Okay. But remember, more amperage, more danger, and more likelihood of a fire or damaging components. Okay. Now, if I looked at the practical, is that we talked about setting up currents at home or circuits at home. Did anybody have any issues with setting up a circuit at their home or during their home practice? Did anyone try to use the switch? No. Okay. Well, so let's look inside Mr. Burleson's home. Okay. This is my den. Okay. And you'll notice behind me, right over here, I have a light switch. Okay. If I go over here and I flip the light switch, the light turned off. The reason why the light turned off is it's now an open circuit. So in other words, there's a wire that goes from this switch that goes out over there to my circuit breaker, and that wire is hot. It's got a lot of voltage. But right now it's open, so there's no current. So on this side, there's a ton of voltage. On this side, there's no voltage. And then this wire goes all the way up here to the light up above. Okay, and then there's actually another wire that actually runs back to the circuit breakers. Because again, we got to have a place for it to go all the way back. However, when I flip this switch, it goes from infinite resistance or open circuit to very small resistance and a closed circuit. Now, the electrons can easily go through the switch and easily then go through the filaments inside my light, which are acting as a resistor. And those particular filaments in that light up above, okay, those particular ones are designed such that when electricity flows through them, they heat up to a certain wattage. Remember how those resistors were a certain wattage? Well, that light bulb's a certain wattage. And that filament inside there is designed such that when it gets hot, when it's excited by the electricity, it glows. And that's how it creates the light. Now, when we get to LEDs, we'll talk about how LED lights work. And they use a lot less amperage, so they use a lot less power, but they can produce a lot more light. And then, of course, incandescent bulbs, what they do is that they actually excite the gas, or excuse me, CFLs, compact fluorescent light bulbs, or fluorescent lights actually have a gas inside the tube, and then they get high voltages at AC, and they excite that gas, and that's how they create the light. So that is the way that switch works. But what I'd like everybody to do is to go to the website or go to your computer, bring up a web page, and then you just can type in simple circuit diagram. And you will notice, and we go here to images, and there's a simple one. And that's the switch we were just talking about. See? I've got a switch, I've got a battery, or in this case, I've got power from the house, and I got a light bulb. And this right here is the simplest of circuits. And this one's going to have a certain resistance, okay? So I've got a V, I've got an R, and since I know the V and the R, I can determine the I. Sometimes the circuits will look something like this, okay? I've got a V, and then I've got 3 resistors in series. Now, you'll notice that it's got the squiggly line here. That means that's 10 volts AC. Now, we're not going to do AC voltage problems. They're done very similar to DC voltage problems, but just they're not done as part of this. But if I just turn this into a DC source, this would be a completely legal question. It would be an illegal question if I kept it as AC. And I look here, and here is a similar, simple, I got a single battery, I've got a switch, it's in the closed position, so it's on, and then you'll notice here, I've got a light bulb. Now, sometimes the battery's gonna be pointed that way. If you remember, sometimes the battery's pointed the other way. It doesn't matter, it just reverses the current. And generally speaking, with most DC light bulbs, they don't care which way the current's flowing. You get the same current going through the same resistor, it heats up the same way. All right, we've come up to about the end of the hour. Are there any other questions? Okay, so please study for the next one. We're going to get into parallel circuits, and we're also going to get into kitchen batteries. And that's one where I will really recommend that everybody, if you can, get together with your coach, get together with your mom or dad, go out, get some potatoes or a lemon or 2, or some Coca-Cola or something like that. You can go and get galvanized steel wire like this. I just bought this at Home Depot. So this is going to be my steel wire. And then I went out and I got some copper wire. Okay, but you can get copper wire as well at Home Depot. If you get steel and copper, that's usually good enough. I mean, if you want to get aluminum, you can do some experiments that way. But then follow the rules that you find online for creating kitchen batteries. And try to create a 1-cell, a 2-cell battery to sort of show how you can create batteries in parallel, okay, or series. We never create batteries in parallel, and we'll talk about that next time. Are there any other questions? Okay, everybody. Well, I want to thank you all, and I think we had a really good time. And if you think of anything else, feel free to reach out. Take care.